Hey everyone, today I'll be talking about my project on lesion detection. This was an effort that span across a college semester at SJSU. Here's a glance of the team, and I'll be talking about the progress as well as progress that was achieved after the semester ended. So here's an overview of what I'll be talking about today. So the problem that we're facing, that we're looking to overcome with lesion detection, has to do with colorectal cancer. And back in 2020, it was reported over 900,000 people died from colorectal cancer, and that includes colon cancer. So what we see here is the large intestine, and then there's an area there populated with what are lesions, typically polyps. And that's what we'll be combating against. So one of the procedures that we can use to deal with these lesions is called endoscopy. And this requires using a flexible tubing device that's called an endoscope that has a light, camera, and a tool typically known as a cutter that are at the end of it. And so what a doctor or surgeon will do is they'll put this into the human's mouth, going through past the esophagus, into the stomach, into the upper intestine. And with this, we can use the camera to pass frames to our lesion detector to find potential cancerous polyps or not. And the other procedure is called colonoscopy. And this is actually the one that's for our use case. And so what this procedure goes through is taking this flexible tubing device, and instead of going through the upper, what's called the gastrointestinal tract, we go through the lower gastrointestinal tract. And that's going into the human body through the anus with this tubing device. And then the surgeon maneuvers the device throughout the large intestine, looking for potential polyps that are cancerous. And the goal here is that we run our lesion detection pipeline on frames, as well as ideally on real-time video. So here's a breakdown of our ML-Dev pipeline. We started out by collecting raw data, and we got this data from various colonoscopy videos that were done in different environments. And you can imagine there's many frames that are extracted from these videos. And then we do feature extraction, we evaluate our features for the sake of, will the features in the images be well suited for training our model? We then perform transformations on the images, such as data augmentation, and then we build and train our model, and then we evaluate it further. So a glance into our data set. So University of Kansas collected over 200 videos of colonoscopy procedures, and they got the sources from these different databases. And at the end, they were able to come out with a data set that was close to 40,000 frames. Here's a glance of our data of the polyps, and we wanted this to be as close to real as possible. So we see there are multiple bumps, and these are the polyps, and different angled views. And for this process, the University of Kansas got 3 endoscopists to label these images. Here is what our annotation file looks like. So these are the labels. This is done in what's called Pascal Voc format. Typically, it's used, makes it easier to train object detection models. And here we can see the first box shows the polyp name, adotomatous, aka cancerous. Alternatively, there's hyperplastic, and that's non-cancerous. And then we have our bounding box coordinates. So the data preparation, part of our pre-processing pipeline included resizing images, so 128 by 128, and that was for our polyp classification model, the custom one. And that was so we could go through all of the data set. And what I did, I'll get into that in a moment. We also looked at resizing the images to 192 by 192. That was more specific to YOLO and UNet, which future down the line for the project will most likely change those to be 128 by 128 as well, because we got good results with the custom CNN classifier. And images, typically the bigger they are, the more processing power required by GPUs and computer CPU. And normalization was done on a scale from 0 to 1 instead of 0 to 255. And that was so that the pixels could be within a centered range to prevent the gradients that are required for training the machine learning model, to prevent them from going out of scale. And what I found with the data set was there were actually more labels than there were actual images. So I also removed excess labels. And another technique I used was data augmentation before training our custom CNN classifier. So here you can see a distribution between hyperplastic and adatomatous after the data augmentation was performed. So this was done on 15,000 of the training images out of the overall 28,000 plus training images. And what we came out with was having 28,000 data augmented images. And so we can see the distribution between hyperplastic and adatomatous is pretty well balanced out for the data augmented data set. And for YOLO, there was actually a ton of data prep involved before actually getting to training the object detection model on our custom Polyp data set. So what I did was I created a Python preparation pipeline so that future cases when I need to go through training this object detection model on the custom data set, such as Polyp or another one, I have Python code in a Jupyter notebook that makes it very easy to walk through the steps of running the Python code and automating the whole preparation that's needed before we actually get to training the YOLO model. And it makes it a smoother process, I found. So for instance, we're given Pascal Vogue annotation format, and YOLO expects it to be in YOLO formatted labels. So part of the pipeline, what it does is it does the conversion, and then it also auto configures the hyperparameters of YOLO. It creates the necessary files, and it also structures them in the expected structure format that YOLO requires. And then we get on to actually building YOLO in the Python prep pipeline. And then there was some parts of it that I couldn't do in Jupyter that I could do in a Python script. But for the sake of the Jupyter notebook and making the steps easier to follow, I shared run this particular command in the Windows command prompt in order to say train the Darknet model on the YOLO, on the Polyp images. However, again, this part could also be automated if we, instead of using Jupyter Notebook, we run a Python script. So there was some feature engineering that was involved for the UNet model, and part of that was our data set didn't come with any segmented masked labels. So I had to go out and create 200 of these masked labels. And also these are binary images. The binary images that you see on the right there are the labels that are required to train UNet. So I had to go manually mask the images. And so starting, I masked 200, but I'm planning to do more. And I also performed data augmentation on the data set. So 200 Polyp images and their binary labels became 5,000 of these images that have rotation, flip, and so forth. Now on to the models. So here we see the architecture of our custom CNN Polyp classifier. So we have a 128 by 128 over RGB image that's passed into our CNN classifier. And we have a convolution layer that extracts out features such as lines and edges of the Polyp images, and then it downscales the images to 124 by 124. And you'll notice here that there are many more channels, and there's 24. And what the convolution layer does is it will output what are called feature maps. And each of these feature maps has on them the edges and the labels. And then max pooling and dropout and ReLU is performed on those feature maps. Max pooling is done to reduce the noise, so then our model can focus on the most important features. Dropout is used to prevent overfitting, helping our model to generalize better on data it hasn't seen before. And so we have multiple convolutions followed by max pooling layers, dropout, ReLU, until we get to the end here where we have dense ReLU and sigmoid. And since we're dealing with the polyp could be hyperplastic or adatomatous, we're doing binary classification. And here's a sample of the model evaluation graph during training. So the accuracy, we can see it's increasing. And as a reminder, accuracy is just all of the predictions that we got correct. So let's say we predicted that a polyp is cancerous. That's true positive. Let's say we predicted that a polyp is not cancerous. That's true negative over all the predictions. And so this is what the graph is showing. And then here's the graph for precision. We also want this increasing as well. And precision takes into account the total predictions that we said were cancerous polyps, and in fact they were, so true positive, divided by that, but then also taking into account the false positives. So those are the cases where we say the polyp is cancerous when in fact it isn't. And so we want this precision to be high, so then that means that those false positives are low. And so as long as our precision is increasing, then we're meeting that goal, as we can see. Recall is similar, except now we're taking into account the false negatives. And so that would be a case where we say, our model makes a prediction that the polyp is not cancerous when in fact it actually is. And so as long as we have high recall, then that number of false negatives will be low. And that's the goal here. And we can see the model during training. The training and the validation recall are increasing, so we're meeting that goal. And now we're on to YOLO. So the difference between YOLO and our custom CNN is that YOLO actually uses all convolution layers, followed by max pooling and so forth. At the end here, we even have a convolution layer that outputs our prediction. So in this case, it'll output the classification and it'll output the bounding boxes, the bounding box. And in configuring YOLO's hyperparameters, we in fact set what the output is going to be of that last convolution layer. And we also set what the input image size is going to be for that starting layer. So for the case of YOLO, I trained YOLO on our Polyp dataset over 6 hours on the original 7,000 images. This was not data augmented images. It was the original 7,000 training images from our training set. Again, that's 7,000 out of 28,700 plus training images. And also remember, the YOLO expects its particular labels in a required format. So that was done. And then the results, some of the results that I saw during training was the mean average precision achieving 83% with a loss of 0.3 and 0.4. So in the case of UNet is, as you can see, U-shaped. And what we have is we have multiple convolution layers that the image gets passed into, followed by max pooling, followed by convolution again, max pooling. So what we can see is we're downscaling the images. And in this case, with convolutions and max pooling, the effort is to extract out the most important features to help us identify, and in the case of UNet, segment the polyp in the image. And then we actually upsample on the right side of the U. And so what that does is, after we've extracted out the insight we needed from the images, now we have to display it in a predicted image. And so that's the segmentation part. And in the case of UNet, after masking 200 polyp images with the original two, each having their own particular original image, I did data augmentation to get 5,000 masked images, each with the associating image, polyp image, and then I achieved a UNet valid accuracy of 94%, 31% loss, and IOU score of 74%. Here we can see some evaluation graphs that are showing, in this case, during training, the loss. So we want our loss to decrease during training, which is what we're seeing. The IOU score is something very important in object detection as well as image segmentation. And what this shows us, the equation here, is the area of overlap divided by the area of union. So that's intersect over union. And how we can tell if we have a model that's great at detecting or segmenting images is this score, this value will be above 0.5. And what that'll look like in the case of the images here, the boxes, they'll be closer to intersecting. So they'll be closer together the higher the IOU scores. And we can see the IOU scores increasing in our graph. So here's some of the results. So we can see that the YOLO detection model got what we were expecting, with bounding boxes at their appropriate location for majority of the images, and the classes identified for each polyp, atomicist, or hypoplastic with the confidence score. And then in the case of UNet, we see we have our original image and then it's segmented, but there's still some work that can be done there too. So one of the things that I was running into difficulties with was running predictions on the images and getting the output, the expected output. And I think part of that may be I need to mask more images and I need to do more data augmentation. And then I also have to have a bit better understanding of how to go about doing the predictions with UNet. So for displaying our app, for a user interacting with our app, the goal here was for a doctor, surgeon, some care provider to have easy access to it. And so for that, we found Rasa to be very helpful, because Rasa is a conversational AI platform used for conversational AI. You can use it to enter text, you can use it for voice recognition. And so the goal here was to deploy our models that we just talked about into this AI platform. And then other part was to display the text and the images. We wanted to display it in a nice graphic user interface, but also eventually to the point where we can do simulation with it. And so we chose Unity, since Unity would offer a nice transition eventually from 2D to 3D. Evaluating the models. So here are some important key terms: accuracy, precision, recall we've talked about. Here's again a quick review of that. We'll just glance over it. So here we can see the evaluation table for our CNN model. Again, precision, recall. We're focusing on the testing row. We can see our precision is high at 76%, recall is 90%, accuracy is 82%. Again, as a reminder, I took a fraction of the original training set of images and took out 15,000 images and then performed data augmentation to create 28,000 data augmented images. And I used those augmented images to train our custom CNN model to get these results. For the case of YOLO, I used a fraction of the training set, 7,000, and that again was from the original training set. And then for the table here, each row is showing a particular model based on its iteration, or epochs is what some call it. YOLO will end up saving models over time based on once it's met 100 iterations, then 1,000 iterations, 2,000 iterations. And I've seen in some readings that the way YOLO describes iterations, people also recognize as epochs. So just a heads up there. And so what we can see here is we're focusing on the models that have the best precision recall and average IOU. And the detection time is pretty key for reaching real time. So we can see precision is pretty high on the first and the last model at 75%, and then recall is 60%. So we could still do a bit better there. I can increase the amount of images from 7,000 to 14,000, and I can do more training. And then for the average IOU, we can increase that as well. 54% is a bit low. So we want to increase how well the bounding boxes are predicted for their location. UNet. So I took 200 images, masked images, and I augmented them to be 5,000. And the results here that we got were 94% for accuracy. Now, accuracy isn't super important in segmentation models because we could be talking about the accuracy of the pixels that we're detecting. And there's excess amount of pixels. So what we really care about is the IOU score. The IOU score is at 73%, but as we saw in the model visualization, it wasn't represented because we'd expect a high IOU score to have better segmentation result. So that's still a work in progress. So some of my takeaways from the project were that when required to do your own mask labeling for an image segmentation model and train it well and have great results, it's very challenging. And manually segmenting images or masking images is a tedious process. I used my Matplotlib's widget called Image Segmenter. It would help to have tools we can use to automate masking images for segmentation models, and I know those are in works with technology such as Mon AI. And then another area here is comparing YOLO object detection to UNet segmentation. Given that our data set had Pascal Voc annotation labels right off the bat, we were able to achieve better results with YOLO object detection. So there's still work in progress for UNet, which I'll be doing research into on my own time. And then I was able to leverage Rasa Conversational AI platform and Unity game engine to create a nice way for a surgeon doctor to interact with the application here for lesion detection. And the way that I deployed the CNN model to Rasa, our custom CNN, was just using TensorFlow's Keras API. And then in the case of Darknet, I did try TensorFlow at first, but I compared how long it takes to run object detection, and Darknet itself running at the C API can do object detection within 5 seconds, whereas TensorFlow, it takes at least 20 seconds to run it. So it's a bit of time, and so I stuck with using Darknet directly. And good thing here is OpenCV has a way to just load in the Darknet model directly, and so we're able to use OpenCV to deploy Darknet that way for YOLO Polyp detection. And so UNet is still a work in progress with integrating it into Rasa. Future enhancements. So I'm looking at testing out real-time classification and object detection. I'll be simulating colonoscopy images into videos through taking those sequence of frames and recreating the videos from them. In the case of the validation and test set, their folder structure is named based on the video that they originally came from. So I can just create some simulated videos out from those. And then there's some further integration that could be done with Rasa, and the video segmentation piece is another one that I'm interested in doing later on. time for the demo. I'll be showing you guys Rasa Unity Polyp classification and detection. So here I have Unity game engine. I have my chat window. Just for you guys to see, I have two terminals here. So this one is going to run the Rasa run server. This is what's going to be communicating with Unity game engine. And there's also another Docker container running in the background called ngrok, and that actually any messages that Unity sends to Rasa will actually go through ngrok, which ngrok will forward them to Rasa, and then Rasa will send back messages and say the classification report, object detection report, and ngrok will forward that back to Unity to be displayed. So our model is in the process of loading, and then Rasa run server is about to run. I'm going to now, I have another Docker container for running Rasa run actions. And so what this focuses on specifically is making sure that these Rasa custom actions are running. So we see there's a few of them. The ones we'll be focusing on in the demo is the run image classification and the run object detection. Those two work. And video detection is a work in progress, and so is image segmentation. Okay, our Rasa server is running. We're going to start the application, and so we can just go straight to it. I want a patient Polyp classification report. So we'll send it. Okay, so Rasa lets us know what the patient IDs are and which one do we want for the classification report. And we can say 1. Okay, so what we see here is patient Polyp classification ID 1 and actual and predicted. And then we can say again, I want a patient Polyp classification report. So we can ask Rasa this multiple times. And so what I'm doing is I'm clearing the Rasa slot so that we can come back during the same time, the same session, and ask Rasa for more patient classification reports. So now we're going to say patient 3. So again, we're deploying our model here. We can see that this Polyp image is aautomatous actually, and the prediction is aautomatous. Now let's get on to the object detection part. I want a patient Polyp detection report. So now this is going to run Darknet using OpenCV integrated with Rasa custom actions. And in this case, let's start with 1. Okay, so in this case, if there's no bounding box and there's no class shown, then that would mean that the confidence threshold and pretty much the thresholds weren't met that were required to draw out the bounding boxes. So sometimes that happens with images. So we can just ask again for another patient object Polyp detection report. So 3. So we can see here that the polyp in this image is hyperplastic and there's a bounding box around it. We can for now ignore the noise. That would be bounding boxes, of course, that are not actually representing polyps. So let's do another one. I want a patient polyp classification detection report. And so we can say, let's try 6. So we can see that's hyperplastic drawing around this box, and this is a different illuminated image, and RGB values are different for it. As we can see, it's green colored instead of the other one being more of a pinkish color. That has to do with lighting. Let's do one more. I want a patient polyp detection report. Okay, and so what we can say is we can do a 9. So nothing. Let's do one more. Polyp detection report. And this is where I was talking about too. Need to further train the YOLO detection model. Okay, let's do one more. I want a patient Polyp detection report. Okay, so let's try 4. Nothing. I want to see if I can get at least one that is automatous. Let's try 5. Yeah, so here we can see this bounding box is automatous, and the class in fact is there, and it does look like it would be a cancerous polyp. So thank you guys for tuning in, and hope you enjoyed the demo as well as the presentation. Oh, actually, if you guys are interested, real quick, I could show you the custom actions code that was used for integrating in the models. So I have here the actions Python script. And so here we have our action run image classification class. And in the case of Rasa, it'll take a name for that class because we end up using it in the stories and the domain. And if you're interested in Rasa, I would just look at the documentation. But so for the integration piece, I'm using multiple helper methods: get file paths, read image, get images, get text label, get XML label names. And majority of the work is happening inside this run method. This is unique to Rasa's custom action class, so this run method. And so what we can see here is I get the CNN file. So this is our saved CNN Polyp classification model. Verify the version. I load the model, and then I bring in one of the images, test images based on the patient ID that we passed to Rasa from Unity. And then I do some pre-processing on the image. And then I also get the label. So we can, in the case of classification report, show the actual label and the predicted label. So I do some pre-processing on that, and I use the label encoder. And then I run the prediction on the Polyp image. I get back what the classification is for it. And then I end up plotting it using matplotlib. And so that's where I show the Polyp image and the actual and the predicted label. And then in the case of Rasa, we have to save the image, and then we pass the we pass the image file path to Rasa, and we do it in a message. And then Rasa will send that to Unity. And then in the case of Unity, what I'm doing over there is I'm taking that file path, I'm creating the absolute file path from it, from my computer, and then I'm reading that in, which I can briefly show you guys as well. But first I'll go through the run object detection custom class, because both of the same cases are happening. I'm passing the image file path for the object detection model. So again, I have similar helper methods, and then I have the method that in this case does the most work is the CV YOLO detect method. So that CV stands for OpenCV. And so in this case, for YOLO, there's a few things we need to pass to our model before we can, before we can read from it. So we need our hyperparameters. So that's defined in the YOLO v4 custom configure file. And then we also need our weights path. The weights is throughout training, what YOLO does is it saves weights. Those are just like saving instances of the model. And so from having both of those from having both of those paths specified, we can pass that into OpenCV's deep neural net, read net from Darknet. And so CV can directly read in the Darknet YOLO model. And so that's what we do. We get Darknet model. We then also get the Polyp labels from this object names file. We get some test images. In this case, we're going to get one for the patient ID. And something that I should note here too, similar that I did above, I grab a random frame from that particular patient's set of frames. Because again, remember, each patient ID correlates to a video, colonoscopy video, and there's a full set of frames there. So we can just take a random frame and then use that random frame from the video to report on, here's the object detection. And so I also get the test annotation file. I do some label encoding with that. So that's for the Polyp label name. And then this part here getting into blob from image, setting the input, layer outputs, and each output detection we're doing. What we're getting is we're going to get the confidence scores, compare that against our threshold we set, because we want to make sure that we're getting the highest or the best predictions from our object detection model. And so we're saving bounding boxes based on those highest confidence levels. Bounding boxes as well as class IDs. And then out of those set of bounding boxes, confidence scores, what NMS boxes does is it grabs the best one. So then we loop through the best ones, and then we end up getting our Polyp labels, and we're just checking, is it adatomatous or hyperplastic? And then instead of using matplotlib, I'm using OpenCV2 directly to draw the rectangle and its coordinates, and also place onto the image the text. So in this case, whether it's hyperplastic or adatomatous, and since we're in this section here, we'd be writing adatomatous. And then here's a part, the CV2 put text that I commented out, but it could be good for measures if we want to do debugging, where at the top of the image, we report on how many polyps are, or how many cancerous polyps are identified in the image, how many non-cancerous polyps are identified in the image, and it'll show that count. Resize the image so that it fits better in our Unity chat window. And then I save it and then return it. And we're in now the run method, again, core part of Rasa's custom action. And again, get the patient detector ID, similar idea as the classification custom action. And then I run YOLO detection, and then I pass it the file path of our predicted image that's been saved. So the detection image that's been saved. And then again, I'm resetting the patient ID. So real quick, going to Unity. So the way that Unity does this, yeah, so Unity sends the message that we write to Rasa. Okay, we receive the message from Rasa, set image text from URL. So that was something provided, but something that wasn't provided was set image texture from PC. So what I had to do in this case was I had to get the path of where our image is located. So again, these are the predicted images. And then I had to read all the bytes. And then I had to wait to get the bytes. And then I'm creating a texture 2D you can think of as an image. And in this case, it's just a blank image at this point, with the default, or it's sort of like some dummy parameters. I'm setting it to 128 by 128, but the actual image that I load in, if the dimensions of the image are different, it'll just overwrite those preset dimensions. And then we got some debug logs there for verifying the text width and height of the image. And then the sprite actually converts the texture 2D to an image that can be displayed in our chat window on Unity. And we run that in a subroutine where we start coroutine, to refresh the chat bubble position, and that's what gets displayed in our Unity project. So thank you guys for your time. I hope this was helpful. Again, this is Rasa, Unity, and TensorFlow, OpenCV, YOLO, with deploying models across these different systems. So thank you again for your time.